Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. Presently we are studying Marine Auxiliary Systems and Tech Machinery. Today we have ninth lecture and the topic is Introduction to Heat Exchangers. In this tutorial, we will first discuss about the definition of heat exchanger and various functions for which it can be used. Then we will discuss about different purposes for which heat exchangers are used on ships. Next, we will discuss about the cooling and heating mediums used on ships in heat exchangers. Then we will discuss about the classification of heat exchangers. Next, we will learn about the modes of heat transfer utilized in heat exchangers. Then we will learn about the factors responsible for heat transfer. Next, we will learn about the flow of fluids in heat exchangers. Lastly, we will compare the temperature profiles in parallel and counterflow heat exchangers. Let us discuss these through the following slides. Introduction. What is a heat exchanger? Heat exchanger is a device which is designed to transfer heat between two fluids. Which are the processes where heat exchanger can be used? Heat exchanger can be used for processes such as cooling, heating, condensation, or evaporation. What is the mechanism of heat transfer? The basic principle involves the transfer of thermal energy from one fluid to another, usually without the fluids coming in direct contact with each other. Which factors are responsible for efficient heat transfer? The direction of flow, the surface area of contact, and the temperature difference between the fluids play crucial roles in determining the efficiency of heat transfer in a heat exchanger. Uses of heat exchangers on ships as per heat exchange processes. Cooling. Cooling may be required for lowering the temperature of engine cooling water, lubricating oil, combustion air for diesel engine, compressed air, control air, hydraulic oil, or drinking water. Heating. Heating may be used for increasing the temperature of heavy fuel oil, feed water and combustion air for boiler, sludge for incineration, lubricating oil during purification, cooling water for preheating engine, hydraulic oil for warming up, seawater during tank washing, domestic water for bathing, and LNG while discharging. Condensation. Condensation is required for exhaust or excess steam in steam plant, liquefaction of refrigerant vapors in refrigeration plant, or evaporated seawater in freshwater generator. Evaporation. Evaporation is required in refrigeration plant, freshwater generator, or vaporization of LNG fuel. Cooling and heating medium used on ships. For cooling, Seawater is the primary cooling medium on ships or large systems. Low temperature freshwater. In order to reduce the size of seawater system due to its corrosive effect, low temperature freshwater system is used on modern ships as an intermediate cooling fluid. Air. Air is used as cooling fluid on small systems. Water-cooled heat exchangers are much smaller in size as compared to air cooling because water can absorb 4.23 times more heat than air for the same mass of both fluids. At the same time, seawater temperature is usually lower than atmospheric air temperature, which further improves the heat transfer. For heating, steam is the primary heating medium on most ships. Thermal oil. Thermal oil is also used on some ships. Seawater. Seawater is occasionally used for heating LNG during its discharge. For condensation. Seawater. Seawater is used for condensation of steam. Low temperature freshwater. Low temperature freshwater is nowadays used for condensation of vapors in large refrigeration and air conditioning systems. Air. Air is used for condensation of vapors in small refrigeration and air conditioning systems. For evaporation. Air. Air is used for evaporation of liquid refrigerant in refrigeration and air conditioning systems. Diesel engine cooling water. Diesel engine cooling water is used for evaporation of seawater in freshwater generator on motor ships, although steam is used for this purpose on steamships. Steam. Steam is used for vaporizing the LNG as fuel in boilers and diesel engines. Classification of heat exchangers. Heat exchangers can be broadly divided in the following two categories. Surface contact type. In these heat exchangers, the two fluids are separated by a surface. Direct contact type. In these heat exchangers, the two fluids come in direct contact, which are usually miscible with each other. Most of the heat exchangers on ship fall in the category of surface contact type, which can be further divided in following three categories. Shell and tube type. Shell and tube type heat exchangers are generally used for exchange of heat from liquid to liquid, as in case of coolers, vapor to liquid, as in case of condensers, and steam or thermal oil to other liquid, as in case of heaters. Shell and tube type heat exchangers can have different arrangements with single or multi-pass and parallel or counterflow which can affect the heat transfer efficiency or the selection of material required for their construction. Plate type. Plate type exchangers are generally used for exchange of heat from liquid to liquid. Fin and tube type. Fin and tube type heat exchangers are used where one of the medium is usually air or flue gas which flows over the tube carrying either liquid or vapor. Air or gas is usually forced across the tubes. Direct contact type heat exchangers are used for following purposes. Feed water heater. Feed water heater in large steam plant utilizes the extracted or bled steam from propulsion turbines. Feed water deaerator. Feed water deaerator in large steam plant is used for removal of dissolved oxygen by heating the feed water with exhaust steam. Spray type desuperheater. Spray type desuperheater is used in moderate size steam plants for desuperheating the live steam before dumping in vacuum condenser while spraying the feed water. Refrigeration plant dual cooler. Heat of lubricating oil in refrigeration reciprocating compressor is taken away by direct contact between refrigerant and oil. Refrigeration plant cooling tower. Cooling towers are used in large refrigeration installation on land where air is forced to flow over sprayed water to cool it down. In addition to heat taken away by the air, part of the water also evaporates, which further removes the heat as evaporation of each kg of water takes away approximately 2394 kilojoule of heat from remaining water. This is helpful in reducing the cooling water temperature, thereby lowering the refrigerant condensation pressure. Hyperbolic cooling towers. Similarly, direct contact heat exchangers are vastly used on land in large thermal power plants as hyperbolic cooling tower, where air naturally flows over the sprayed cooling water and takes away the heat. Modes of heat transfer in heat exchangers. It is important to understand the theory of heat transfer and the modes by which heat is transferred in heat exchangers. Heat exchange between two fluids separated by a wall takes place in three stages. First fluid transfers the heat to one side of the wall convectively, then the heat is transferred by conduction to the other side of the wall, and finally the heat is transferred convectively to the second fluid from the other side of the wall. Convection heat transfer. Convection heat transfer between a fluid and a metal wall is given by Newton-Rickman's law and is expressed by the equation Q convection is equal to H into A into Th minus Tc, where Th is the temperature of the hot fluid in Kelvin, Tc is the temperature of the wall in Kelvin, A is the area of wall in meter square, and H is the coefficient of convective heat transfer in watt per meter square Kelvin. Conduction heat transfer. Conduction heat transfer is given by Fourier's law and is expressed by the equation Q conduction is equal to K into A into dt by dx, where A is the area through which heat exchange occurs in meter square, dt is the temperature difference in Kelvin, dx is the thickness of the material in meter, and k is the constant of thermal conductivity in watt per meter square Kelvin. Factors responsible for heat transfer. We have observed from the above equations that heat transfer is directly proportional to the surface area and temperature difference across the two fluids and inversely proportional to the distance between them. Heat flow through a circular tube is given by the following expression. Q is equal to K into 2 pi RL into dt by dr, where R is the radius of the tube, L is the length of the tube, dt is the difference in temperature, dr is the thickness of the tube, and K is the coefficient of thermal conductivity in watt per meter square Kelvin. Surface area. Increase in tube radius and its length increases the surface area and hence the rate of heat flow. Large diameter tubes may be suitable in low pressure applications, but they become unsuitable in high pressure application due to increased tube wall thickness, which reduces heat transfer. In such cases, large number of small diameter tubes can be used to have required surface area. Tube surface is usually extended with fins, pins or gills to increase the heat transfer when fluid outside the tube is air or gas. Circular tubes are preferred over other shapes due to strength reasons, although they provide the least surface area. Sinusoidal tubes are sometimes used in heat exchangers which are difficult to clean. Length of the tubes are usually between 5 to 15 times the diameter of the shell. Wall thickness. Lesser wall thickness improves the heat transfer, but it increases the stress which may cause rupture of the tube. Reduction of the tube diameter reduces the stresses acting on the tube wall. Thus, for keeping the stress within limits, tube thickness can be reduced, although tube diameter below 10 mm is not suitable. Temperature difference. Higher the temperature difference across the surface, faster is the heat transfer rate. High temperature difference across the surface can also cause thermal distortion of the material. Superior material should be considered to prevent this problem. Fluid velocity to the tube. Laminar flow with velocity below 1 meter per second slows down the heat transfer rate and causes deposits on the tube walls. On the other hand, turbulent flow improves the heat transfer and prevents deposition of the debris associated with the coolant on the tube walls. However, velocity exceeding 2.5 meter per second causes erosion of the tube material, which should be avoided. Coefficient of thermal conductivity. Thermal conductivity of the tube material also plays a very important role in the heat transfer process. Copper has the highest coefficient of thermal conductivity with its value of 386 watt per meter Kelvin, followed by aluminium with its value of 205 watt per meter Kelvin. Heat exchanger tubes are usually made up of cupronickel or aluminium brass. Direction of flow in heat exchangers. Effectiveness of the heat exchanger is largely dictated by the flow path within the heat exchanger, whether parallel flow or counter flow. which is discussed in the next slide. Types of fluid flows in heat exchangers. Each of the flow arrangement have their own merits and demerits. This helps in optimizing the design of heat exchangers and making them light and compact, which serves a unique advantage on ship in maximizing the cargo capacity. Parallel flow. In parallel flow arrangement, both the fluids flow parallel to each other as shown in the figure. In parallel flow arrangement, large temperature difference at the ends causes large thermal stresses which can lead to eventual material failure. The temperature of the cold fluid exiting the heat exchanger can never exceed the lowest temperature of the hot fluid, which is the distinct disadvantage if the design is to raise the temperature of the cold fluid as in case of a boiler. Counterflow. In counterflow arrangement, the two fluids flow in opposite directions as shown in the figure. In counterflow arrangement, more uniform temperature gradient gives better overall heat transfer, produces a more uniform rate of heat transfer throughout the heat exchanger and minimizes the thermal stresses throughout the exchanger. Outlet temperature of the cold fluid can approach the highest temperature, that is, the inlet temperature of the hot fluid, but high mean metal temperature requires high grade of metal. In comparison to parallel flow, counterflow is more efficient. Cross flow. When one of the fluid in the heat exchanger is vapor, generally cross flow is used as shown in the figure. The surface area on the vapor side is usually increased by use of fins to increase the heat transfer rate. Whether parallel, counter or cross flow, heat transfer within the heat exchanger involves both conduction and convection. Heat exchangers are thus designed in such a way that heat transfer is most effective, although the designers have also to keep in mind the safety and reliability of the operation. Comparison of temperature profiles in parallel and counter flow. This figure shows the temperature profiles in the two types of heat exchangers. Because the heat transfer process takes place over the entire length of the exchanger, the temperature of the fluids as they flow through the exchanger is not generally constant but varies in a non-linear way over the entire length. The rate of heat transfer varies along the length of the exchanger tubes because its value depends upon the temperature difference between the hot and cold fluid at that point. A precise temperature change between two fluids across the heat exchanger is best represented by the log mean temperature difference LMTD, which can be expressed by the equation LMTD is equal to delta T1 minus delta T2 divided by natural log of delta T1 divided by delta T2, where delta T1 is equal to the larger temperature difference between the two fluids streams at either the entrance or the exit of the heat exchanger, and delta T2 is the smaller temperature difference between the two fluid streams at either the entrance or the exit of the heat exchanger. Higher the value of LMTD, better will be heat transfer. This completes the study of Introduction to Heat Exchangers. This book is written by me and covers all topics as per the syllabus specified by Indian Maritime University. It clarifies the concepts with simple illustrations. The book also provides answers to all the questions which have appeared in the examination conducted by Indian Maritime University. The book can help the students in preparing for the exam and also to work on ships, auxiliary systems, and deck machinery safely. Hope that you have liked the lecture. You can write your feedback in the comment box. If you have liked the tutorial, you may share it with your friends. You must subscribe to the channel for getting notification about the new tutorial. I will be back with a new lecture shortly. Thanks for watching till the end.